DART has dominated the news cycle this week, and today is not any different for us. We'll have an interview with Amanda Sickafoose about her observations of the spacecraft's impact from the South Africa Astronomical Observatory later on in the show. We're also going to cover a couple of stories that relate to just why this mission is important. Asteroid impacts and all that. We're also going to talk about how accurate a new machine learning algorithm is at finding gravitational lenses and how a quasar has helped uncover evidence of a Gen 1 star. Oh, and some astronauts returned to Earth. All of this and more today here on the Daily Space. Pamela is still battling her injury, so I am your host, Beth Johnson. And we are here to put science in your brain. Today's top story is the publication of 68 confirmed gravitational lenses from a subset of 77 candidates drawn from a list of 5,000 candidates found in the Dark Energy Survey and Dark Energy Camera Legacy Survey by neural networks. This represents an 88% success rate. These lenses use gravity to bend light toward us that would normally travel to other parts of the universe, thus magnifying what we see. Since galaxies are lumpy but gathered into roundish clusters, these magnified galaxies appear as distorted arcs. This work is published in the Astronomical Journal with lead author Kim V. Tran. She explains, quote, "Our goal with AGEL is to spectroscopically confirm around 100 strong gravitational lenses that can be observed from both the northern and southern hemispheres throughout the year." End quote. Since telescopes are unevenly distributed around the world, this kind of positioning allows for continuous observations. Galaxies can be lensed multiple times, and any flicker that can be observed in multiple lenses can tell us about the light path of each lensed galaxy and about the changing geometry of our universe. Here is to hoping this team has clear skies and time on big scopes to see this project succeed. I'm not sure I actually have the language to express how exciting this next story is, but I'm going to try. According to Carl Sagan, quote, "If you wish to make an apple pie from scratch, you must first invent the universe," end quote. Well, one of the early steps in making that universe is making stars. We have been searching for evidence of those first stars from the moment we realized our universe had a time zero. And we have been failing to find them for about a century. That changes today. A team led by Yuzuru Yoshii has identified a supernova remnant that is chemically consistent with its forming when a 150 to 300 solar mass star exploded. That first-generation star was made only with the atoms made during the Big Bang. This nebulous gas was found in the outskirts of a distant bright galaxy. The light we are seeing comes from when the universe was less than 1 billion years old, and what we see so far matches the models we hoped were right. This is just one object, but it shows us, finally, that these things can be found, and now I'm sure this team and others will be looking for more. While we wait, let's turn to Eric with astronauts coming home.
Late Wednesday night, the crew of Soyuz MS-21 packed up their spacecraft and undocked from the International Space Station after a several-hour-long leak check. The moment of undocking marked the beginning of ISS Expedition 68, commanded by ESA astronaut Samantha Cristoforetti. After several more hours coasting away from the ISS, because you really don't want to fire your rocket engine near the station, the Soyuz conducted its deorbit burn. This burn lasted 5 minutes, after which the Soyuz separated its orbital and service modules and oriented for re-entry. 1 hour later, the capsule landed on the cold steppe of Kazakhstan, a few hundred kilometers from the town of Zhezkazgan. All Soyuz capsules and other Soviet/Russian recoverable capsules have landed in this area. The all-Russian crew of Soyuz MS-21 returns after 195 days in space. 2 of the members completed their first flights into space, and the last, Oleg Artemyev, completed his third. Artemyev and cosmonaut Denis Matyev conducted several spacewalks together to prepare the European robotic arm on the Nauka module for operations. Artemyev did 33 hours of spacewalking across 5 spacewalks, and Matyev did 26 hours across 4. Sergei Korsakov did not perform any spacewalks during the mission. With this successful landing, there are again 8 toilets and 7 humans in space, so that will be back to 9 toilets again shortly with the launch of SpaceX Crew 5. That launch was expected on October 3rd, but has been delayed as Casey is experiencing the impacts of Hurricane Ian. The Falcon 9 rocket and Crew Dragon capsule for that mission are both safely inside the Horizontal Integration Facility at 39A, which is built to survive the expected conditions. And now, back to science.
When we talk about planetary defense, especially in the context of the DART mission, mass extinction events such as the Chicxulub impact tend to come up in conversation. That particular event involved an impactor about 10 kilometers in diameter, which left a crater 180 kilometers across. Not only did the dinosaurs die off, other global effects included atmospheric heating, forest fires, acid rain, basically global devastation. Hence the importance of the DART mission. And it's easy to focus on that one single event as being a reason to work toward planetary defense, but Chicxulub was by far not the only impact, or even the largest. That designation goes to the Vredefort crater in South Africa, which up until recently was thought to have formed by an object measuring 15 kilometers in diameter. Now, in a new paper published in the Journal of Geophysical Research and led by Natalie Allen, computer simulations based on new geological evidence have upped that estimate to between 20 and 25 kilometers. Estimating the size of the original crater, and therefore the size of the impactor, is a difficult process due to the erosive properties of our planet. The crater is 2 billion years old, and that is a lot of erosion to account for. The new evidence supports an original size of 250 to 280 kilometers, and the simulations show that the object had to have been traveling at 15 to 20 kilometers per second to leave such a huge crater. Upon impact, dust and aerosols would have spread in the atmosphere, blocking sunlight. As for what was living on Earth at that time, co-author Miki Nakajima explains, quote, "Unlike the Chicxulub impact, the Vredefort impact did not leave a record of mass extinction or forest fires, given that there were only single-cell life forms and no trees existed 2 billion years ago. However, the impact would have affected the global climate potentially more extensively than the Chicxulub impact did." End quote. On top of there not being a lot of biological evidence of the Vredefort impact, the locations of land masses 2 billion years ago would have been vastly different. Error bars on just what that looked like get larger the farther back in geologic time simulations go. But this new research could provide a better understanding of the makeup of the ejecta and how far it might have traveled after the initial impact. Finding that ejecta around the world would make it easier to create a more precise picture of the Earth at the time. Once again, we remind you that there are presently no known asteroids greater than 140 meters in size that are known to be a threat to Earth for at least 100 years. All of the research into craters and asteroids helps us understand the potential threats that are out there and what effects they could have on our world. Research into impact events doesn't only involve craters here on Earth. A new study in Science Advances analyzed lunar glass brought back by the Chang'e 5 sample return mission and found that what we thought were just major events on Earth were actually accompanied by smaller impacts on the Moon. Researchers studied the glass beads, which were up to 2 billion years old. Sound familiar? Using a variety of techniques, including microscopic analysis, numerical models, and geological surveys. Lead author Alexander Nemchin notes, quote, "We found that some of the age groups of the lunar glass beads coincide precisely with the ages of some of the largest terrestrial impact crater events, including the Chicxulub impact crater responsible for the dinosaur extinction event. The study also found that large impact events on Earth, such as the Chicxulub crater 66 million years ago, could have been accompanied by a number of smaller impacts. If this is correct, it suggests that the age frequency distributions of impacts on the Moon might provide valuable information about the impacts on the Earth or inner solar system." End quote. Next up, the team wants to compare the Chang'e 5 data with other lunar soil samples and crater ages. Maybe we can even further constrain when the Redirection impact occurred. Coming up next, my pre-recorded interview with scientist Amanda Sickafoose about the DART impact and the images collected in South Africa. It all ties together today. Stay tuned. On Monday, September 26th at 2314 UTC, in front of a global audience, the Double Asteroid Redirection Test, or DART, successfully hit the tiny 160-meter asteroid Dimorphos. Numerous telescopes around the world and in space, including the South African Astronomical Observatory, all had their instruments turned toward the collision. Joining us today is Amanda Sickafoose, a senior scientist at the Planetary Science Institute, who was conducting the observations at the SAAO. Thank you for joining us today, Amanda.
It's really nice to be here, Beth.
So yesterday was a bit wild. Tell us about it. What was it like from your end?
A lot more exciting than I expected. That sounds awful. And we were talking about this before we started. I've had very little sleep. It's been a really exciting night and a long trip back. I actually drove back from Sutherland to Cape Town today. I had kind of geared myself up for it might get a little brighter. You know, we might not see very much because you never know what's going to happen. And it was just phenomenal. I mean, you were watching the images come in. You saw as the Draco camera was taking those. We had the live stream of the Draco camera on one screen. So we were watching Dimorphos get closer and closer and closer and just gasping out loud at what we were seeing. And on our screen, we were watching the images from the telescope coming in. And that 30-ish second delay between when Draco went dead and when we started seeing something on our screen, that time of light travel. And it got a little brighter and it got a little brighter and we're all staring at it. What's it doing? And suddenly, right, we see these kind of the plume coming off the front and there's all this structure and it's just unbelievable. I mean, it was, I've never seen anything like it. It was
it was amazing. And I was astounded just from the images I saw from Draco as we were getting closer and closer to that surface. And you know, we stopped basically interviewing people. We were just watching it come in and commenting on the different boulders we were seeing and all the features and like, oh, is that a crater? You know, and it was amazing. And then I saw just this morning that SAAO posted their image, you know, a first GIF of what they saw. Atlas did this last night, and it's amazing how similar those two images are. So it you know, this really happened.
Oh yeah, in real time we saw this big thing come off and kind of push forward and move out, almost like you know, like pushing up against the sound barrier or something. Like I never expected anything like it.
No, it was incredible. And to see all of the images coming in real time, close to real time, and then to see all of the things that have been coming out later. So are there any follow-up observations that the SAAO is doing?
So we are continuing. In fact, after we stopped, we did high-speed cadence for about an hour. And, you know, after that, you know, things had settled down and, you know, that the original dust plume that we saw kind of had faded into the background at those exposure times. So we continued taking light curve data in 3 filters, just cycling through G prime, R prime, GR and I actually, GR and I primes, at kind of a longer cadence, 20 seconds. And we're going to do the same thing tonight for the entire time it's visible. So as long as we have good weather, we should get, you know, a 6 or 7 hour stretch of, we had been leading up to this just taking data in one filter with the idea of helping with determining the light curve orbital periods from the light curves. And in this case, we're opting to go with filter cycling because we're thinking that might help tell us a little bit more about the dust. If there is dust, we could see kind of different color trends. And we're going to have a long time from now to be working out the orbital period. That's the big question everyone wants to know. And it'll take a while, I think, to figure it out. But for now, I think we'll do, 3-color imaging, just cycling through those as long as we can.
What do you think is the best takeaway from this event so far? I mean, there's a lot that's going to be coming out of this, but what's the biggest takeaway from it at the moment?
Wow. Well, I mean, one, we did it. We proved we could do it, right? I mean, that's huge. There's a lot of technology. I can't even talk. There's a lot of technology advancements going on, right? If you read the DART literature, and just proving that we could even do this, and proving that we could get all of these people coordinated to be observing in the days and months and years leading up to it, and then going on forward. That's huge. The thing that blew my mind and that I didn't realize until a couple weeks back was that nobody had seen Dimorphos before.
That's true.
Right?
That's true.
And it was not until an hour before the event, when the spacecraft is showing, here's Didymos and here's this little moon, that that's Dimorphos. We knew it existed because of the light curves. So we inferred that the moon was there. We sent a $330 million mission to a moon that no one had ever seen. And then we crashed into it.
I mean, it's so dead on target. It was astounding. It's like you're just watching these images coming in, and the ground is literally approaching you. And it's like this is the first time we've seen this poor little moon. We've just crashed something into it. We didn't really have like good pictures of Didymos to begin with. Everything was sort of radar images and infrared and not a lot of detail. And all of a sudden, as we're approaching, we're like, boulders, look, oh, it's definitely a rubble pile. Oh, this is, and it was just, it is kind of amazing when you think about everything that had to go into that. And of course the spacecraft was acting at this point autonomously. Like the whole thing was, okay, we're on approach. We see Didymos. Now we're just waiting for Dimorphos to come into view. Now we have to track it, lock onto it, and aim for it. And it all worked.
I know. and we as scientists are sitting there a couple hours beforehand, and we're turning to each other going, so how do they know that they're pointing at Dimorphos and not Didymos, right? How does that work? Who does that? And then we're watching interviews on the NASA live feed of the people at APL who have programmed this stuff, and we're going, this is amazing. The people doing this stuff, it's absolutely amazing. Yeah. One other thing I was going to say, something I haven't done before with observations like this, the DART team had a Slack channel, and it's a big team, and so again, almost in real time, because we're taking data and I'm furiously, downloading it and modifying it and, making light curves and whatever. People are posting, little GIFs we had posted the GIF of the plume, and, so did Alan Fitzsimmons from Atlas. And so real scientists on the team were all commenting back and forth in real time. And boy, was that fun. And people I haven't talked to in years. And I'm like, oh, I know that. Oh, right. He's saying hi and she's saying this, and wow.
So I'm looking forward to all of the imaging that's going to happen. And of course, we have the follow-up of Hera coming up in a couple of years. So how involved do you think you're going to be in the research going forward? Or is this pretty much, we've taken our images and I've got to go run off on like 7 other projects now?
Yeah, I mean, we're basically ground-based observing support here. So I'm happy to be involved. We're not funded to be working on DART, but we have a small active asteroid group here. So we actually, well, I was the one planetary scientist, and I've brought, Nick Erasmus came on a few years back. I actually pulled him out of laser physics. That was a win for planetary. But we were working with John Tonry to get the Atlas telescope here. So that's now up and running. So, but there aren't a lot of people here who do planetary science. That's pretty much it. So Nick works at the SAO, and I obviously work for PSI remotely. So if there are supporting things we can ever do, I feel like our niche is, we have this great site. We were talking last night about how unbelievably dark it was last night. They have laws in place to protect from sky light pollution. So we have a great site. We have easy access to moderate sized telescopes, meter class telescopes. So if there are ways we can help, we're always happy. And we do have that tie kind of to the asteroid community because of some of the research we do. But no, I mean, I'm just ecstatic to kind of be one of these people going, well, I can add a little bit to the puzzle and then I can hand it off to the experts and they can do their thing.
All right. Well, Amanda, thank you so much for coming and talking to me after our very long day yesterday and very sleepless night last night. I'm looking forward. I think we have shared the SAO images out that came out already on social media. So for those of you who are listening or watching, you can go check out at CosmoQuest X, and you can see what they've shared between Atlas and SAO and Lycia Cube. It's all amazing, phenomenal, astounding, exciting. Go take a look. And if you were watching any of the live streams yesterday, thank you so much for your participation. And we hope, as scientists, as science communicators, we all hope that you enjoyed it as much as we did, because we definitely enjoyed it. So thank you once again, Amanda, and have a wonderful rest of the time. Good luck on the occultation and get some sleep.
Thank you, Beth. You too. Cheers.
Bye. This has been The Daily Space. To all of you watching, our pre-recorded interview ran longer than we can air here on Now Media. You can catch the conversation in its entirety on our website, dailyspace.org. While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.